Hi everyone. In this video we're going to talk about the electron capture detector, or the ECD, often used in gas chromatography. Unlike the TCD, which was universal, and the FID, which was really good at responding to hydrocarbons, the ECD is going to be the most selective detector that we've seen so far. It's selective toward compounds with electronegative functional groups, such as the ones shown here, and oftentimes compounds with these types of functional groups are of interest from an environmental perspective. For example, pesticides like lindane or polychlorinated biphenyls, which were used as insulators, and a few other pesticides. Look at all of these electronegative functional groups, all of those halogens. Again, the ECD does not respond to any of these compounds, making it not universal, but we're really more interested in its selectivity. So let's talk about how the ECD works. Here's a diagram from your SCUG text. Notice we have a positively and negatively biased electrode, and here is our flow from the column. In addition to that, we also have flowing into the detector some nitrogen. And what does this nitrogen encounter? Well, it encounters this nickel-63 foil, which is radioactive and emits beta particles. If you don't remember what a beta particle is, it's an energetic electron. So imagine all of this nitrogen gas coming into the detector, and it's getting hit with these energetic beta particles. And what happens? The nitrogen gets ionized. This is the electron ejected from the nitrogen, and that is called a secondary thermal electron. And you may be thinking to yourself, well, why did this beta particle stay so energetic? Wouldn't it have lost some energy through this reaction? And actually, it really doesn't lose that much energy. One of these beta particles can produce many of these so-called secondary thermal electrons. So now we see that ions and electrons are produced as a result of this radioactive beta emitter. So what you have here is a burst of electrons, or really you can think of that as a little plasma. So this is what is happening when mobile phase is flowing through the detector. You've got this background plasma that's conducting the current across these two electrodes. Yes, that's what we see here. But then our solute enters and something is going to change. And remember that our solute has these electronegative functional groups that are going to capture some of these electrons. So now we have fewer electrons here in this plasma, and that's going to, well, let me ask you, how is that going to affect the ability of that plasma to conduct the current across these two electrodes? Or in other words, what do you think happens to the current with fewer electrons here? Well, I think you're probably right. You probably guessed that that current decreased. So that's the response that we're measuring. The main advantage of the ECD is that it has very good limits of detection, even better than the FID. And we already talked about how it was the most selective of the detectors. Some of the disadvantages are it has a limited linear range, only 2 orders of magnitude. Water and oxygen also capture electrons, meaning that your sample and carrier gas have to be very pure. And using chlorinated solvents, for example, dichloromethane, during sample prep, like say if you were doing an extraction, could be a problem. And the question is why? Well, if you have any traces of this solvent in your sample, it would also capture electrons and maybe give you a false positive. So that's it for the ECD. Thanks for listening and hope you enjoyed the video.